to see you. Okay, so our last section, so we started talking, we have done the briefest of brief overviews about statistics and what it is. And I told you there was statistics, studying it is broke up into different areas. So we talked about real briefly about gathering data. We talked about the different sampling techniques. So when it comes to the test, I'm going to have a few multiple choice problems that mirror what we did in class, that you have to pick which of the sampling techniques is it. Then statistics also talks about organizing the data. So we talked about frequency distributions and the graphs that go along with them. Then statistics also talks about analyzing the data. So all we did here in this class was the 4 different kinds of measures of center as far as organizing. And there's other things. We didn't talk about how to measure how spread out data is, whether it's all clumped together or whether it goes broader than that. And where we're going to end our time is just talking a little bit about curves, because if you do study statistics, what you begin to find is populations. If you have a big enough population, you develop what's called a continuous distribution. So you wouldn't like have a bar graph, you would have an actual curve. And so the first type of curve that I just mentioned, just to give you an idea of what I'm talking about and how they can be used, is what's called the rectangular distribution. Our book calls it the rectangular distribution. Most books call it a uniform distribution because the reason it's called that is because you can see on this graph that every observation occurs at the same frequency. Okay, so that's why it's called a rectangular or a uniform distribution. So each value occurs with the same frequency. So they're not super common, but the value in being aware of the uniform distribution, especially as you go and study statistics, is there is a relationship, as I've said before, between the area under your curve and the probability that something happens. And so what you'll learn if you do at some point go take a statistics class is, so you have your whole range of values from this low value down here up to the top. And if you want to know out of that whole range of values, what's the probability that like something from, let's say, I'm just going to from here to here happens, then what you would do is you would calculate calculate the area of this little bit. And so for a rectangular distribution, the area of a rectangle is length times width. So it's a fairly easy proposition and a good entry point into probability and area and statistics. But like I said, they're pretty rare. They don't occur like naturally a lot. So then what you do is you get to other types of continuous distributions like the ones below. So there's a couple different types that we're going to talk about. So these next ones are what's called skewed distributions. And you are going to be responsible for a little bit of the information about the skewed distribution. I'll tell you exactly what you need to know. But the reason they're called skewed is because the bulk of your values occur in this part of the curve, but then you have this tail right here. So you have these values that seem to be different than what you would consider the norm of this distribution. So this right here, what I've just circled, this is the skewed. Those are the skewed values. And that's why that first curve is called skewed to the right, is because the tail is on the right. So what you have is you have these values that are larger than the bulk of the curve. And so what it does is it skews everything to the right. Now, what do I mean by skews everything to the right? Well, that's a great question. And so remember, this is a great question for review. Here's the highest point of my curve. This is the most frequent right here. Okay, the highest point of the curve is the most frequent. What's the measure of center? Does anyone remember? We talked about it last week. What's the measure of center that measures what happens with the most frequency? The mode. Sure, mode means most. So what we have here is I'm just going to draw this dotted line. This value on the x-axis, that would be the modal value because it happens with the most frequency. Now, again, this is great review. I hope you did your homework. Remember, each of the measures of center, pardon me, is measuring something a little different. So the mode measures the frequency of things, what happens with the most frequency. The next measure of center divides our observations. Half are above this value, half are below. Does anyone remember the name of that measure of center? What was that? The median. Yeah, the median divides divides your distribution or your data into two equal parts. And so because we have this tail, right, this skew, my median, my halfway point is not going to be right here at the mode. The median gets skewed a little bit. So I'm just going to approximate. And so here is my median, x with the squiggly. So remember, so now my x with the squiggly, this value, half of my observations are above that value, half of my observations are below that value. And then lastly, I tried to draw a picture for you last week and to indicate what the mean measures. And if you remember, the mean measures that the mean is the value that has the same amount of distance to the values below the mean as the distance to the values above the mean. And we talked about the firefighters in our example last week and their ages, and there was just as many years below the mean as there were above the mean. And again, because of this tail, now what I've done is I've increased the distance to these observations out here. So what that does is it skews the mean even more. So there's my X bar. So what I need you to know going into the test and going into the final exam, because this becomes a question on the final exam for whatever reason, is the difference between a skewed to the right curve and a skewed to the left curve and the order of your mean, median, and mode. So the mode becomes the smallest, and then the median's next, and then the mean is skewed the most. It goes toward the tail the most. And then the same thing is true, but in the opposite direction for the curve that's skewed to the left. So I've got my tail here on the left. And so again, I've got my most frequent observation here at the peak of the curve. So that's my most frequent, that's the mode, but this time the tail's going to the left, so that's going to skew my observations, my next two to the left. So again, the median that divides the curve into two halves comes next, and then my mean is the last one because of the tail, and there we go. So when it's skewed to the left, when you have this tail of observations that are smaller than everything else, the mean becomes the smallest observation, followed by the median and the mode. So when you do your homework, you take your quiz, that's going to be reinforced. Just look at that picture, try to have that in your mind, and then you'll be all set when I ask you the same thing on the test or when it's on the final exam. Now that's fun, that's great stuff. But what we're here for and how we're going to end our time together is we're going to talk about what's called the normal distribution. When you take statistics, the normal distribution pops up a lot. If you study anything in biology or economics, things tend to be, for whatever reason, normally distributed. Sometimes the normal distribution is called the bell curve because of its shape. Looks like a bell. And so on that picture that is on the screen or you're looking at on your page, all that is an example of 5 different normal distributions, just to give you an idea that your bell curve can be kind of narrow, like this red one. So right here is we've got data that it doesn't have a wide spread. So this is kind of a narrow curve. And then you can see the purple one, if I can draw an arrow to the purple one only, that purple one doesn't get near as high, but it's very spread out. So this is a very broad curve. And then the yellow one, the blue one, the green one, they're all kind of the same. They just have a different center. Now, the fun stuff about the normal distribution, and the reason that it gets used a lot is, for instance, you probably have some experience with the normal curve, you just don't know it. most of you, I'm guessing, is sometime in high school you took either the SAT test or the ACT test, right? Well, those are examples of what's called a normalized test. And what that means is, and we'll talk about this in a minute, the population of people who take that test form a normal curve. And then your score is given with respect to the population. So whatever value you got in the mail, or I guess email, I don't know how they send it out. Back in my day, it was snail mail. However you got your results, your score was compared. So your results on the SAT are not, you got 5 wrong, so you get 95%. That's not how it works. You got 5 wrong. Well, then what other percent of people got 5 wrong or more? You're compared to the population. We'll look at that in just a minute. So I've put a blank normal curve right at the top just to talk about a little bit of the properties of this. So again, just like we saw with the skewed distribution right here, this is my most frequent. It's the top of my curve. Okay, so my most frequent. So we know that that's the mode. But here's the nice thing about the normal distribution. Thing that makes it a little easier to study. Notice where my mode is. It looks to me like I've got 50% of the values or half the curve on this side and 50% of the curve on this side because it's shaped like a bell. It's what's called symmetric. I don't know if you've encountered or are familiar with the word symmetric. Symmetric just means that it's the same on both sides. Okay, so we've got 50-50. So this dotted line that I've drawn is also the value for the median. Then again, the mean measures the distance of your values. So since it's symmetric, notice I have a value here and I have the same value over here. So they cancel each other out. So down here, we can do that at any point on any y value. Got a point here and here, so they have the same distance left and right everywhere. So that means that this dotted line that I've drawn, the one that's vertical, is also the value of the mean. So the mean, the median, and the mode are all the same value on your normal curve. Even beyond that, okay, no matter how spread out your normal curve is, so whether it's the narrow one that I pointed out, the red one on the previous page, or whether it's broad and spread out like the purple one on the previous page, every normal curve adheres to the following principle. This is called the empirical rule. I think I spelled empirical right, but forgive me if I didn't. Okay, this is called the empirical rule. Now I have to introduce you to something. This would, if we had gone into this a little bit deeper in section 12.4, we would have talked about how to measure how spread out the data is, and we would have come across something called the standard deviation. All I need you to know about the standard deviation is the standard deviation tells you how spread out the data is. So the standard deviation all this does is it's a value that tells you how spread out the data is. So the smaller the number, the more clumped together the data is. The larger the number, the more spread out it is. So in my red curve, my narrow curve, this would have a small standard deviation. And the purple curve, the one that's very spread out, that would have a large standard deviation. So my whole goal here is I'm just trying to develop a little interest in this and to tell you a little something about the normal curve without us actually having figured out how do I calculate the standard deviation. That's something that you'll talk about in whatever statistics class in the future that you go ahead and take. For now, all I need you to know is that there's this thing called the standard deviation, which measures how spread out my curve is. But once you know that, okay, there's this thing called the empirical rule. So this dotted line in the middle, I just told you this is my mean. I'm just going to label it. That's my mean. And each of these other dotted lines represents a standard deviation, whatever the value is. So for instance, this next dotted line is the mean plus, and I'm just going to use the letter S for standard deviation. That's one standard deviation. The next dotted line is the mean, x bar, plus 2 standard deviations. We've gone 2 hops, 1, 2, away from the center of the curve. And this last little tiny dotted line right here is the mean plus 3 standard deviations. We can do the same thing going below the mean. So this first line to the left is the mean minus 1 standard deviation, x bar minus s. This next one is x bar minus 2 standard deviations. Again, I've gone 2 hops from the middle of the curve. And then the last one is x bar minus 3 standard deviations. Again, if I start at the mean, I've gone 3 hops to the left. We're going to put some numbers to this to hopefully make this make a little more sense in just a minute. But before we do that, I just want to tell you, what is the empirical rule? Well, the empirical rule says this. No matter how spread out, no matter how narrow your normal curve is, if you go 1 standard deviation in each direction, you'll always find 68% of your data within 1 standard deviation. So the bulk, okay, the majority of what you're talking about is found within 1 standard deviation. The empirical rule also says if you go 2 standard deviations in each direction, well, 2 standard deviations in each direction, 95% of your data or your observations will be within 2 standard deviations. So what's that mean as far as probability? It means if I'm in a population and if I grab a sample, or excuse me, if I grab a piece of data out of it, I've got a 95% chance, or 0.95, that it's going to be within this range of values right here, from 2 standard deviations below to 2 above. Just this last one, I'm going to do underneath so I don't make an even bigger mess of my curve. Now, the empirical rule says one more thing. If you go from 3 standard deviations below to 3 standard deviations above, then what the empirical rule says is that 99.7% of your data is found within 3 standard deviations, or almost everything. So it's almost a certainty that you're going to get data that's within 3 standard deviations of the mean. So what statistics people say is if something occurs in one of these tails, if something occurs beyond 3 standard deviations, that's called a rare event. Now we could, if we had more time and we could talk in a little more detail, we could say, okay, since the normal curve is symmetric, we can talk about how much area is in each of these parts of the curve, but that's not what we're going to do today. We're just going to finish up our very brief survey of the normal curve by putting some numbers to this as an example. So for instance, here's my example. Then I've got a couple for you to do. This is what I'm going to have you do on the test. Okay, so there's going to be a problem exactly like what we're doing right now. Okay, so just keep that in mind. So example 1, back in 2014, this was the last time I Google searched this, the mean height of American men was 70 inches with a standard deviation of 4 inches. Okay, so what that means is that right here in the middle, the mean height of American men was 70 inches. And what we're going to do is we're going to label the normal distribution. So this is the first skill that we're going to have today. So how spread out the data is each standard deviation is 4 inches apart. So what that means, let's do the ones that are larger. If this is the mean, what am I going to label this first standard deviation? Yep, 74 inches, fantastic. And then what is the next one going to be? 78, and then finally 82 inches, great. Going smaller, below the mean, this one's going to be, I'm going to subtract 4, I'm going to get 66 here. 66 inches, then I'm going to get 62 inches, and then finally 58 inches. So this gives us now, according to this data, it gives us some perspective of how spread out I would expect heights of American men to be. And so you would get a different mean, just as a timeout, you'd get a different mean and standard deviation if you stratified the sample. Remember, we talked about what it means to stratify things. So if I just looked at, white American men or African American men or Chinese American men, and we just stratified it, they'd all have different means and standard deviations. This is just the conglomerate, everyone. So you can find some interesting statistical things. So now we're going to answer just some basic questions looking at this. So what percent of men have heights between 62 and 78 inches? So from 62, which is right here, to 78, which is right here. What percent according to the empirical rule? Yep, so 95%. So in the United States, 95% of men are between 62 and 78 inches tall. So now this time, if I randomly select 750 men, so however I choose to do that, how many would I expect to have heights between 66, so here's 66, and 74? How many of the 750? Well, how am I going to calculate this? What am I going to do? Great. I'm just going to say this again so that anybody that's watching the video can hear, but you said that way better than I can. What she said was to find the percent that are from 66 to 74, which is 68%. So we're going to multiply by 0.68, and then we multiply by the 750 men sample size. And when I throw that down in my calculator, everybody got a calculator handy? What do we get when we multiply those two numbers together? 510? Beautiful. Thank you very much. So what I would expect in my random sample to have right around 510 men that are going to be from 66 to 74. Last but not least, what is the range? What is the height range that contains 99.7% of American men? I'm sorry, what'd you say? Yes, that is indeed true. So 99.7, that is 3 standard deviations, according to the empirical rule. And so that, according to my diagram, is 58 inches to 82 inches. Fantastic. Well done. Now, again, this is not an object for our class, but it's, when you talk about the normal curve, there's all sorts of fun things you can do. You can then figure out, like, if you have one particular value, how it compares to the population. So, for instance, I'm 6'3". So I am 75 inches tall. So I, the Perkster, would fall right here on this. And we can calculate, there's a huge chart. Again, we're not talking about it. I can now calculate how much of the population I am taller than, okay, according to this. And what that would be called is something called a percentile. So if you've ever heard that word percentile, okay, so if you are in, for instance, if you ever took a standardized test and you were in the 80th percentile, what that means is you scored better than 80% of other people. That's what it means to be in the 80th percentile. Just as an example, Shaquille O'Neal, he is 7 feet 2 inches, I believe, if I'm remembering my basketball trivia. So 7 feet 2 inches, 7 times 12 is 84, 86. So Shaquille O'Neal, he's like a full nother standard deviation above. He's a rare event, right? To be 86 inches tall is an extremely rare event. So if you are if you know how tall you are, you can figure out how you compare to this 2014 population. And it's only been 8 years. Populations don't change that dramatically in less than a decade. In 100 years, the mean and standard deviation might be significantly different. Like if you go back 100 years, you know, because of different nutrition and eating habits, people tended to be shorter. So that would be different. All right, so let's go to example 2. Same thing, except this time I looked up the statistics for American women in 2014. So do the same thing, label the normal curve for me and then answer the questions, and then we'll compare notes in a few moments. All right, so labeling my normal curve here, the mean for women is 65 inches. So you can see statistically women tend to be a little shorter than men. Doesn't mean that, you know, statistics is not saying that a woman can't be taller than a man. It just says that the populations have these slightly separate curves. They'll overlap, but in general, we have slightly shorter. And then also the standard deviation is 3.5 inches. Women are slightly, the curve is slightly narrower. There's not as much spread. It's not super significant. It's not like the standard deviation is 1 inch or something like that. So the ones above are going to be 68.5 and then what, 72. Make sure I'm doing my adding right. And then 75.5. Did I do that okay? All right, and then smaller, I'm going to have 61.5, and then I'm going to have, what's the next one going to be? Is that going to be 58? And then subtract 3.5 more, and it's going to be 54.5, I believe. Okay, so here's the answer to the question. What percent of women have heights between 61.5 and 68.5? So that's these two. That's one standard deviation each direction. So hopefully you wrote down 68%. If I select 1,200 women, how many would I expect to be between 58 and 72? Well, that's 2 standard deviations in each direction. So that's 95% or 0.95 of my 1,200. And what is 95% of 1,200? Okay, so 1,140 of the women that I randomly selected would or should, according to the empirical rule, fall into that constraint. And then what's the height range? That's 99.7. Well, 99.7, that's, I'm just going to write 3 here, 3 standard deviations. So that's going to be 54.5 to 75.5. So again, if you know your height, like the super hot Mrs. Perkster, she is 4'10". So Mrs. Perkster's right here. So she is a full 2 standard deviations below the mean of American women, and I was one of, or a little more than 1 above. So we create quite the sight, the pair of us. So there you go. So the last problem I have for us about the normal curve, just as an example, if you took the SAT, each part of the SAT is normalized in the following way. Okay, so if you took the math or you took the English part of the SAT, then the mean is 500, so the score right in the middle, and then the standard deviation is 100. So what it means is you get normalized, and that just means your score is then compared with the population. So what I want you to do, please, is just do the same thing again for this. We're going to pretend it's the math portion because that's the portion I did good on. So go ahead and label the normal curve and answer the questions that you have right there. Okay, so here's the numbers. The mean here is 500. So again, how is that picked? Well, however many right or wrong that means, it's going to be 500 is labeled that point where half the people scored above, got fewer wrong, and half the people scored below. That is how that would be picked. And then we have 600 and 700. Now on the SAT and the ACT, you can't get above an 800. So I know that there's a little area in the tail, but when you normalize something, you can pick the end. And so that you can't get below 800. And similarly, when you take the SAT, you can't get below a 200 on each individual part. So the scores range from 200 to 800. Why were those the values that were picked? I have no idea. I do not know much about the SAT other than some of the basic statistics behind it. So what percent of the results are between 200 and 800? Well, that's 3 below to 3 above. So that's 99.7%. If we randomly select 350 test takers, how many score between 400 and 600? Well, 400 and 600 is one standard deviation in each direction. So that is 68% of the 350. And what is that value? Okay, 238. And then finally, what is the score range of 95% of the results? That's 300 to 700. So for me, I was back then, when I took the SAT on my math part, I got a 780, so I did pretty good. Happy, still proud of that. But then apparently I could barely speak, so I got like a 480 on the English. So just like me and my wife have big differences. I have a big difference in my ability to use the English language. I don't know if they still put them on the SAT, but the thing that got me, okay, they used to have these questions, the comparison questions. So they would say something like desk is to carpet as hand lotion is to what? And then they'd give you your choices, and I'd be like, I could talk myself into every one of the choices, like somehow. So I got like 0 of those right. So anyway, it's a personal problem.